In this lesson, we're going to look at Group 1, the alkali metals. And the first thing I'd like to do is to take 5 minutes to complete this bubble map with everything that you already know about the alkali metals from Year 7 and Year 8, and think particularly about the chemical and physical properties that we think that the alkali metals might have. Now, before we go over the bubble map, I want you to watch the demonstration of the reactions of lithium, sodium, and potassium with water. You can use the periodic table to fill in the symbols for these 3 alkali metals. I want you to watch the videos to take down their appearance of these 3 alkali metals and your observations of their reactions with water. So the first metal we're going to look at is lithium. So here we have some lithium, and it's coated in oil because it's quite reactive. And if we didn't coat it in oil, it would just really readily react with the oxygen in the air. Now, if we take a closer look at it, it's this really sort of dark grey colour. But in reality, that's just the lithium oxide that is on the coating of our lithium. So the lithium atoms on the outside of this block have reacted with oxygen in the air to form lithium oxide. If we cut it in half and expose the middle, we'll be able to see the shiny lithium. Now, if I were to leave this just out in the air, it would start to go that dull, dark grey colour again. So again, the dull, dark grey colour is the lithium oxide, but if you cut into it, you can see the shiny lithium, and already it's starting to dull. I'm not sure if you can see it very well on the camera, but it's already starting to go grey. It's reacting with the oxygen in the air to form lithium oxide on the coating again. So we're going to look at the reaction of the alkali metals with water. And when you react a metal with water, or certainly an alkali metal with water, you get 2 products. You get a metal hydroxide and you get hydrogen gas. So what we're going to expect to see is some bubbling from the hydrogen gas, and the metal hydroxide will turn our universal indicator purple, because hydroxide ions are what cause solutions to be alkaline. So you can look at the water, it's ever so slightly green. I'll add a little bit more. It's got universal indicator in it already, and it's pH 7, so it is green. And when the hydroxide is formed from the metal reacting with the water, that will start to turn purple. So we're looking for the universal indicator turning purple because of the metal hydroxide being formed, and we're expecting to see bubbles of gas from the hydrogen being produced. So if we drop in a piece of the lithium that we cut just a minute ago and observe the reaction. So again, you can see you've got the bubbles of gas being produced, which are hydrogen. And if we look around, we're starting to see this purple colouring from the universal indicator, showing that we have an alkali being formed. So if we drop the second piece in, just to repeat that, you can see the bubbles of gas being given off, which are hydrogen gas. We can see the universal indicator turning purple, showing the presence of a hydroxide. So this was lithium, so the reaction is lithium reacting with water to form lithium hydroxide, which is causing the universal indicator to turn purple, and hydrogen gas, which explains the bubbles of gas being produced. The second metal we're going to look at is sodium, which again, if you look at it, it's this very, very light grey colour. And once again, it's stored in oil to try and prevent it from reacting with the oxygen in the air. But as you can see from this light grey colour, it has reacted with the oxygen in the air because it is very reactive. And just like before, if we cut into it, inside you will see the shiny sodium metal on the inside. So just like with the lithium, it's got this coating on the outside where it's reacted with the oxygen in the air. It's very, very soft. I mean, I know I'm using a scalpel, but it's a very blunt scalpel. And if I wanted to cut a block of iron, I wouldn't get anywhere with a scalpel. So for metals, they are very, 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 very soft. They're very reactive. They're reacting with the oxygen in the air, causing them to have this sort of dull oxide coating on the outside. But if you cut into it, you expose the shiny metal on the inside. So we're going to look at the same reaction, but this time with sodium. So we're going to add our universal indicator to the water. Again, the water is pH 7, so it's going to be green. But by adding sodium to water, we are going to get sodium hydroxide and hydrogen gas. And the hydroxide is going to cause our universal indicator to turn purple, and the hydrogen gas is going to cause fizzing. So when we add our sodium, what we should notice is it's reacting much more aggressively. Now, where it's moving, you can see, wherever it's moved, you can see that purple change of color for the universal indicator, indicating that we have a hydroxide being formed. So that would be sodium hydroxide. You'll also notice it moved around much more aggressively. So it's reacting more vigorously, much more reactive than lithium. And also, when we put the lithium in, the lithium stayed in the shape that I cut it. But look at the sodium is turning into a ball. And the reason it's doing that is because it's reacting so vigorously, it's giving off a lot of heat energy, and it's actually melting the sodium. So the sodium that's fizzing around on the surface there is actually a molten ball of sodium. It gets so hot that it melts, and then it sort of fizzes around on the surface in a sphere. So I'm just going to put the last piece in there. And again, you can see turns into a ball, fizzing around much more vigorously, but you are getting the fizzing, the gas being produced, and you can see the changing color for the universal indicator showing that sodium hydroxide was being produced. So finally, we're going to look at potassium. So again, much like with the sodium and the lithium, if we have a look at it, you've got this sort of grey coating, light grey coating on the outside. But once again, if we cut into it, we should expose the shiny potassium metal on the inside. Now notice I've used the back of the scalpel there. I've used the blunt side of the scalpel, and I've been able to cut through that incredibly easily. And inside you have the shiny potassium metal. So just like before, it's stored in oil to try and prevent it from reacting with the oxygen in the air. But the potassium atoms on the very outside, they form that dull oxide coating, so potassium oxide coating. But if you cut into it, you see the shiny potassium on the inside. And if we compare all three of them, they're getting softer. So the lithium I was able to cut with the scalpel reasonably easy. The sodium even easier. The potassium unbelievably easy. Using the back of the scalpel, the blunt side of the scalpel, I was able to cut through that incredibly easily. It's very, very, very soft. So the last reaction we're going to look at is the reaction of potassium and water. And again, adding my universal indicator, which is nice and green because it's just water and it's pH 7. But if I react potassium with water, I should get two products. I should get potassium hydroxide, and the hydroxide will turn my universal indicator purple, and I should also get hydrogen gas. Now we saw both of the previous metals, the lithium and the sodium, both turned the universal indicator purple and produced hydrogen gas. But what we noticed was that the sodium was more reactive than the lithium. It was much more vigorous in its reaction, and it gave off more heat energy because it was able to melt the sodium, whereas the lithium just stayed in the shape I cut it and fizzed around. And the sodium obviously moved around much, much quicker. So if you look at the periodic table and you look at lithium and sodium, you'll see that lithium's at the top, followed by sodium, followed by potassium. So we should see a continuation of that pattern. The potassium will also turn my universal indicator purple because it's going to produce a hydroxide. It's going to give off a gas of hydrogen, but it's below sodium, so we're expecting an even more vigorous reaction. We're expecting the potassium to be more reactive than the sodium. So let's put a piece in the water. And what you saw straight away, much more vigorous reaction. it actually sets itself on fire. So the hydrogen gas that's being produced, it's hot enough to ignite that gas, and it sets itself on fire. So again, much more vigorous, and it reacts much, much quicker. The reaction's over much faster than it was for sodium. So we put the last piece in, you notice it gives off enough energy to ignite that hydrogen gas. So very clearly, we've got the purple colouring from the hydroxide that's being produced. We had the fizzing of the gas, and it got hot enough, it gave off enough energy to ignite that gas. So very, very similar reactions. They all produce hydroxide, so they all turned the universal indicator purple. They all gave off hydrogen gas because we could see the fizzing. And they got more reactive as you went down. So very, very similar reactivity, but they actually get more reactive as you go down that group. So from the periodic table, we can quickly find the symbols for these elements. We've got lithium, Li, sodium, Na, and potassium, K. And it's important that we are checking in the periodic table because obviously Li is the initials for lithium, but Na is not the initials for sodium, and K is not the initials for potassium. So don't assume that you're going to know it. Always check the periodic table, and if it has two letters, the first one is always capital and the second is always lowercase, and if it just has one letter, then that is just going to be capital. So the appearance of these three metals. So we should have seen that the lithium was shiny. However, it had a dark grey coating on the outside. So it had a dark grey coating, and that coating was the lithium that was on the outside that had reacted with oxygen to form lithium oxide. So it had a dark grey coating of lithium oxide. But once we cut into it, the inside was nice and shiny, which is the lithium. The sodium, when we cut into that, that was also shiny, and it had a light grey coating on the outside, and this time that coating would have been sodium oxide. And finally we had the potassium, which again when we cut into it was nice and shiny, but on the outside it had a grey coating, and in this case it would have been potassium oxide. So their observations. So the lithium, it moved around on the surface. It produced bubbles of gas. And we've got to be careful because even if you did know that that gas was hydrogen, you couldn't have said that from your observation. What we saw were bubbles of gas produced. So don't make the mistake of saying hydrogen gas was produced because you can't tell that just from looking at it. So it moved around on the surface, it produced bubbles of gas. The indicator turned purple, and the lithium dissolved. So the reason we got the bubbles of gas being produced was because we had hydrogen gas being produced, and the reason the indicator turned purple is because when lithium reacts with water, it forms lithium hydroxide, and hydroxide ions are alkali ions. So metal hydroxides are alkaline, which is why the indicator turned purple, which is why the alkali metals are called alkali metals, because they form alkali compounds. So sodium, we noticed that the sodium also moved around, but it moved around more vigorously. It also produced bubbles of gas. The indicator also turned purple. But importantly, the sodium turned into a ball. So the lithium, when I put the lithium in, it stayed as the shape I cut it. If I cut it into a cube, it stayed as a cube. But the sodium actually turned into a sphere. And the reason it did that is because the energy produced is hot enough to melt the sodium. So the sodium melts into a sphere. And then it dissolved exactly the same way as the lithium did at the end. Now the potassium was a little bit more exciting. It moved around very vigorously. It produced bubbles of gas. Although to be fair, it was quite hard to see that because the reaction was over so quickly. It was difficult to see, but it would have produced bubbles of gas. The indicator turned purple, showing us that a hydroxide was produced. And importantly, it caught fire, or it ignited. So it ignited the gas, the hydrogen gas that was being produced. So where the sodium was reactive enough to produce enough heat to melt the sodium, the potassium was even more reactive, produced even more energy, and was able to ignite that gas, which is why you saw that purple flame. And obviously at the end, it dissolved. So these are all the different things that we could have put down as our observations with water. Now, because we've done that now, we can go back to our bubble map and start thinking about the properties that we might have thought of before and the things that we've come across in those videos. So, we should have noticed that they are very reactive. Perhaps we noticed that they produce a hydroxide and hydrogen when they react with water. We saw that they all had that coating on the outside because they react with oxygen in the air to form oxides. And we can think, well, why do they have these properties? Why are they shiny? Well, because they're all metals. So it makes sense that they will have metallic properties. Why are they all very reactive? Why do they all react with water to produce hydrogen and a hydroxide? Why do they all react the same way with oxygen? Well, because they have the same electronic configuration. They all have one electron in the outer shell. That's why they have such similar reactivity. So other things that we might expect to see, well, we saw that they were very soft. It was very easy to cut into them. They were shiny when polished. Obviously the outside of them wasn't particularly shiny, but if you polish them or if you cut off the oxide coating, then they would be nice and shiny. They were very malleable. They are good conductors. Of heat and electricity. But we saw that the temperature of the reaction was able to melt the sodium, so their melting points are quite low. So there's a variety of different, in red I've gone for chemical properties and in blue I've gone for physical properties, but a variety of different things that we could say about the alkali metals. So here we have the opportunity to write word and symbol equations for those reactions. Now, because they are all alkali metals, they all have one electron in the outer shell, they're going to have very, very similar reactions. So I'm going to go through the word equation and the symbol equation for lithium and water, and you should be able to therefore write the word and symbol equations for all of the other alkali metals with water just by substituting the metal. So I'm going to go through the word equation for lithium and water, then the symbol equation, and then you should be able to do the same for sodium and potassium. So lithium plus water produces lithium hydroxide, which is why our universal indicator turned purple, and hydrogen, which is what the bubbles of gas were. So our symbols for that, so we've got lithium, Li, water, H2O, lithium hydroxide, LiOH, and hydrogen, H2. And Not that you need to know how to do this at the moment, but we need to balance this. So we want the same number of each element on both sides. So we've got 1 lithium, 1 lithium, 2 hydrogens, 1, 2, 3 hydrogens. So we need more hydrogens on this side. So we're going to have to put 2 there. And in order to make that balance, so 2 lots of 2 is 4. Well, I've already got 2 there, so I can't double that. That'd give me too many. So I need 2 here, which means I also need 2 lithiums. But that should now be balanced. So for sodium and water and potassium and water, it's going to be identical because they're group 1 elements. They all have 1 electron in the outer shell, so they're going to have the same or very similar chemical reactivity. So you just need to substitute the lithium for sodium or potassium, and you can write the word and symbol equations. Once you've done that, there are some questions that you can answer, and then finally a quick double bubble map comparing the reactions of lithium and potassium with water. So what was similar between the reactions and what were different between the reactions, and that should take you about 10 minutes. So for the word equation for sodium and water, we should have had sodium plus water would give us sodium hydroxide, which is why the indicator would turn purple, and hydrogen, which is going to give us our flammable gas. Symbol equation is going to be exactly the same as it was with lithium, but with sodium. So Na plus H2O, giving us NaOH rather than LiOH, and hydrogen gas. And then we're going to balance it the exact same way because it's going to react the exact same way because it also has 1 electron in the outer shell. So potassium plus water gives us potassium hydroxide. Again, that's why our indicator turned purple. And hydrogen, which is the gas that ignited. And our symbol equation, K plus H2O goes to KOH plus H2, and it's going to be balanced the exact same way. So the questions: what was the purpose of adding universal indicator? To indicate the presence of a hydroxide, either the lithium hydroxide, the sodium hydroxide, or the potassium hydroxide, because these metal hydroxides are alkaline. What was the flammable gas produced in each reaction? It was hydrogen. Write a list of the alkali metals that you observed, putting them in order of reactivity, with the most reactive first. So I'm sure we're all in agreement that potassium was the most reactive, followed by sodium, followed by lithium. Extend the list that you have made above to include all of the group 1 elements. So we can see that the pattern is that as you go down the group, they're getting more reactive. So if we look at the 3 that we've got, lithium, sodium, potassium, they're getting more reactive. So we'd expect logically that francium is the most reactive, followed by cesium, then rubidium, and then potassium, sodium, lithium. So francium is the most reactive alkali metal, followed by cesium, followed by rubidium, followed by potassium, sodium, and lithium. So use a double bubble map to compare the reactions of lithium and potassium with water. So they produce hydrogen. They produce a metal hydroxide. What was different? The potassium ignited the gas. The potassium moved more vigorously. The reaction was faster. And with the lithium, the lithium didn't change shape. the reaction was slower. And it moved slower on the surface. Now, what we could also say, they produced a metal hydroxide, so we could also say the indicator turned purple for both. They both produce hydrogen, so there were bubbles of gas produced for both. So we've clearly observed that the group 1 elements have very similar reactivity because they all have one electron in the outer shell, but they don't have the exact same reactivity. And that's because their electronic configuration is not identical. It's similar, they've got the same number of electrons in the outer shell, however they have different numbers of shells, different numbers of electrons in total. So you don't need to just be able to explain the pattern in reactivity, so we can clearly see that they get more reactive going down the group. We need to be able to explain that in terms of the electronic structure. So we're going to start off with the electronic configuration of the first 3 alkali metals. So lithium is in group 2, so it has 2 shells, 2 electrons in the first shell, 1 in the third. Sodium is in period 3, so it's going to have 3 shells, and it's in group 1, so it's going to have 1 in the outer shell, which means that the other shells are going to be full. So 2 in the first shell, then 8 in the second, and 1 in the third. And finally, potassium, which is in period 4, so it's going to have 1, 2, 3, 4 shells, and it's group 1 again, so 1 in the outer shell, and then all of the other shells are going to be full. Remembering that you can have 8 in all those shells apart from the first one, which can only hold 2. So 2, 8, 8, 1. So if we write out their electronic configuration, we've got 2, 1, 2, 8, 1, and 2, 8, 8, 1. So, and we saw very clearly that their reactivity was they got more reactive as you went down the group. So reactivity, clearly, we have more reactive as you go down the group, or less reactive as you go up the group. Now, we need to be able to explain why. Now, when metals react, they're losing electrons. They're losing their outer shell electrons. So we need to consider what's holding those electrons in place in the first place and what's changing as you go down the group. So fundamentally, these electrons in these shells, the reason they are being held where they are is the strength of attraction from the nucleus, because the electrons are negative, and in the nucleus you have positively charged protons. So there's a force of attraction between those positively charged protons and the negatively charged electrons. And that force of attraction is called electrostatic attraction. So when we consider which electrons are being lost, so they're group 1 elements, they're metals. Metals, when they form ions, they lose their outer shell electrons. So when lithium reacts, it wants to lose this electron. When sodium reacts, it wants to lose this electron. And when potassium reacts, it wants to lose this electron. Now remember, the protons are always in the nucleus. The protons are always in the center. And what you notice is as we're going down the group, we get more shells. And if we get more shells, it means that that outer shell electron is getting further and further from the nucleus. And that makes that electrostatic attraction get weaker and weaker and weaker. It's just like holding 2 magnets and holding them further apart. The magnetic force they feel from each other is going to get weaker. So if that force of attraction is getting weaker because there's more shells, as you go down there's more shells, so the outer shell and the nucleus are getting further and further apart, and that electrostatic attraction is getting weaker and weaker and weaker, it becomes easier for the atoms to lose that electron, which is precisely what metals want to do. The easier it is for it to lose that electron, the more reactive it is. So, our explanation, I'm going to write it in two different colours, and I'll make a point of why in a minute. So, the first thing you need to consider, going down a group, the number of shells increases. The distance between the nucleus and the outer shell increases. The electrostatic attraction gets weaker. Okay, so going down the group, the number of shells increases. So going down, shells increases. The distance between the nucleus and the outer shell increases. The electrostatic attraction gets weaker. This is key terminology you have to be using, and the reason I've written this stuff in black is because it doesn't matter which group you're talking about. If we're talking about group 1, this is true. If we're talking about group 2, this is true. If we're talking about group 3, this is true. Even if we're talking about non-metals like group 6 or group 7, these 3 points are still true. So if you're asked to explain the reactivity down any group, then you write these 3 things. Going down the group, the number of shells increases. Therefore, the distance between the nucleus and the outer shell increases. Therefore, the electrostatic attraction gets weaker. If you write that for any of the groups in the periodic table, you are going to be correct. Now, the last thing we need to add is what that means for the group we're actually talking about. And you have to ask yourself a question, because there's 2 ways to end this answer, and it depends. Are we talking about metals or are we talking about non-metals? Because remember, when metals form ions, they lose electrons. But when non-metals form ions, they gain electrons. So you're going to have the opposite pattern of reactivity. Here, we're talking about metals. So we're going to end our answer. Therefore, it is easier to lose electrons. Therefore, reactivity increases down the group. Okay? So the stuff I've written in black is always true. The stuff I've written in red is only true for metals. So if I'm talking about group 1 or group 2, then this is the perfect answer. However, if we were talking about non-metals, and we will come back to this when we talk about the halogens, but if this was non-metals, these 3 things would still be the same, only non-metals aren't trying to lose, they're trying to gain, so we would just have the reverse. It's therefore harder to gain electrons, reactivity decreases down the group, is what we would write for non-metals. But for metals, this is what we're going to write. But importantly, no matter what the question is really asking, if it asks you to explain the reactivity down any group, these first 3 bullet points you should always write, because it's always true. And then you ask yourself the question, is it a metal or non-metals I'm talking about? If it's metals, these are the last 2 points you need to make. So there are a few questions here for you to answer. Should take you about 5 minutes. Right, so the first question, write a word equation for the reaction of cesium with water. So cesium plus water, and we should know this because all the alkali metals are going to react the same way. So we're going to get cesium hydroxide and hydrogen gas. Write a symbol equation for the reaction of rubidium with water. And again, it's going to react in the exact same way that all of the other alkali metals reacted. So we're going to get rubidium, hydroxide, hydrogen gas, and it's going to be balanced the exact same way as it was before. Let's put that N on the end of hydrogen. In terms of electronic configuration, what do all the alkali metals have in common? They have one electron in the outer shell. What charge ion do all alkali metals form? Well, they've only got one in the outer shell, so they form a charge of +1 because they are metals. They lose electrons to become positive, and because they've only got one electron in the outer shell, they become +1. Why do the alkali metals all have similar chemical properties? Because they have the same number of outer shell electrons. Or you could state that they all have one outer shell electron. You'd get the marks either way. So to finish off, you've got a 10-mark facts test. This should take you no more than 5 minutes, so you're looking to answer 2 of these per minute. So you've got 5 minutes, answer these 10 facts test questions. So the first question, what name is given to a substance that contains more than one type of atom or compound not chemically bonded? That is a mixture. How did Mendeleev organize the elements into groups in his periodic table? Similar chemical properties. You could give an example, for example, reactivity. How many protons are in an isotope of chlorine 35? Now, it doesn't matter that it's an isotope because we're talking about protons. So chlorine, whether it's an isotope or an ion, doesn't matter. All chlorines have 17 protons. If it's an isotope, the only thing that changes is the number of neutrons. The proton stays the same. If it's an ion, the only thing that changes is the number of electrons. The protons stay the same. What is the link between group number and atomic structure? Group number is equal to number of outer shell electrons. What is produced when lithium reacts with water? We should get lithium hydroxide and hydrogen. What are elements in the modern periodic table arranged across a period? How are elements in the modern periodic table arranged across a period? So in Mendeleev's periodic table, it was increasing atomic weight, but in the modern periodic table, it is increasing atomic number. But you could also say number of protons. Either one of those is fine. So you can either say increasing atomic number or increasing number of protons because those two things are the same. State the trend in melting points of the alkali metals down the group. It decreases, which we saw because the sodium melted because it has a lower melting point. Name 2 features of the plum pudding model. So we should have sphere of positive charge and randomly scattered electrons. How many protons are in an ion of oxygen? Again, like I said earlier, it doesn't matter that it's an ion because we're talking about protons. The only thing that changes in an ion is the number of electrons. So the number of protons will be the same. So oxygen, atomic number 8, therefore 8 protons. And name 2 features of the nuclear model. So we have dense, positive nucleus and electrons in orbitals. So make corrections in green pen, make sure you've got all of them down, and give yourself a score out of 10.